The topic of this lesson is magnetic field intensity, permeability, and reluctance. Let's examine magnetic field intensity first. The figure shown demonstrates a toroidal ring made of soft iron on which is wound a coil having N turns. A current of I amperes flows through the coil, resulting in a magnetomotive force, MMF, of N times I ampere turns. A magnetic flux of phi Webers will be established in the toroid. If the cross-sectional area of the ring is A square meters, the flux density B is equal to phi divided by A in Teslas. All the flux, however, is not confined to the iron. There is some flux in the adjoining airspace, and this is termed leakage flux. If the ring is increased in diameter, the flux density inside the ring is decreased. The ampere turn is the MKS unit of magnetomotive force and is represented by the symbol denoted by the script F. Magnetic field intensity, H, is called a magnetizing force. It is the MMF per unit length and is equal to ampere turns per unit length. Thus, H is equal to N times I divided by L in ampere turns per meter, or H times L equals N times I. And since the force is equal to N times I in ampere turns, therefore the force is equal to H times L in ampere turns. Permeability is a figure indicating the ability of a material to permit the setting up of magnetic lines of force, whereas permeance is the measure of the ability of a given magnetic circuit to permit the setting up of magnetic lines of force. Permeability is the ratio of flux density to the magnetizing force and is denoted by the symbol mu. Therefore, mu is equal to B divided by H. In free space, mu is equal to 4 pi times 10 to the minus 7th SI units, and B is equal to mu times H. Let's look at an example. What is the magnetomotive force required to establish a magnetic flux of 500 microwebers in an air gap whose length is 2 millimeters and whose cross-sectional area is 5 square centimeters? Since air is non-magnetic, its permeability is the same as that of free space. Therefore, A is equal to 5 times 10 to the minus 4th square meters, L is equal to 2 times 10 to the minus 3 meters, and phi is equal to 500 times 10 to the minus 6th Weber. Flux density is equal to phi divided by A, or 500 times 10 to the minus 6 Weber divided by 5 times 10 to the minus 4 square meter, or 1 Tesla. Field intensity, H, is equal to B divided by mu, or 1 divided by 12.57 times 10 to the minus 7th, which is equal to 0.8 times 10 to the 6th ampere turns per meter. Magnetomotive force, F, is equal to H times L, which is equal to 0.8 times 10 to the 6th ampere turns per meter times 2 times 10 to the minus 3 meters, which is equal to 1600 ampere turns. If we keep the magnetic field intensity inside a coil constant, the ratio of the flux density established in the core material to the flux density produced in a vacuum is called relative permeability and is signified by the symbol mu sub r. For air and any other non-magnetic materials, mu sub r is equal to 1. Paramagnetic materials such as aluminum, platinum have relative permeability slightly greater than 1. Ferromagnetic materials such as certain nickel-iron alloys have mu sub r ranging up to 100,000. Thus, relative permeability mu sub r is equal to mu divided by mu sub 0, or the flux density in free space. Thus, absolute permeability mu is equal to mu sub 0 times mu sub r. Flux density B is equal to mu sub 0 times mu sub r times H with a magnetic core, and therefore phi is equal to B times A, or mu sub 0 times mu sub r times H times A. In a magnetic circuit, there is a constant of proportionality between the magnetomotive force and the resulting magnetic flux. This constant is called reluctance, denoted by a script R, and is equal to the magnetomotive force F divided by flux density phi, or R is equal to F divided by phi. By substitution, R is equal to L divided by mu times A. Let's look at an example. A magnetic circuit has an air gap of length 2.5 millimeters and a cross-sectional area of 10 square centimeters. Calculate the reluctance of the gap and the MMF required to establish a flux of 1,000 microwebers across the gap. Mu is equal to 1, A is equal to 10 times 10 to the minus 4th square meters, and L is equal to 2.5 times 10 to the 3rd meters. Reluctance, therefore, is equal to L divided by mu times A, or 2.5 times 10 to the minus 3 divided by 12.57 times 10 to the minus 7 times 10 times 10 to the minus 4th, or 1.99 times 10 to the 6th SI units. The MMF required, F, is equal to R times phi, or 1.99 times 10 to the 6th times 1,000 times 10 to the minus 6th, or 1,990 ampere turns. Permeance, noted by a script P, is similar to conductance in an electric circuit. It is the ability in a magnetic circuit to permit the setting up of magnetic lines of force and is the reciprocal of reluctance, or P is equal to 1 divided by R.